Section 3-3 is on the derivative functions. The objective of this section is, given the equation of a function, graph the function and the derivative function and calculate difference quotients. We're going to tackle the difference quotients part of this in the next video. We're going to worry about the derivative function here in this video first. All right, let's start out with what's called a numerical derivative. And a numerical derivative, in fact, anytime you see the term numerical, they're going to be referring to doing some calculation on your calculator. All right, and so a numerical derivative is an approximation of a derivative evaluated numerically on the calculator. So, in order to use this command on the calculator, of course, there's got to be a new command that we're going to learn here, and it's called the nderiv command. And the nderiv command, there's actually a couple of different ways that you can use it. I'll go through the two ways that you can use it. First way here is to say nderiv, which nderiv stands for numerical derivative, and then you specify three things. They're called the parameters here, is what we call these three things. The first parameter is the expression. That's if you're given some function and you're trying to find a derivative of that function at a point, then the expression is the function you're trying to find the derivative of. The second thing you specify after the comma is a variable. It's the variable that makes up the expression, whatever variable is that expression is defined upon. So usually that will be x. And then finally you specify a value, and the value is the value that you're trying to find the derivative at. So those three make up our parameters for the nderiv command. Now there is a fourth parameter that is optional. That's why there's two different ways that we can write it, because we can put the tolerance in there or we can actually leave it out. That fourth parameter there is the tolerance. And what the tolerance specifies, if you go back and recall how we were initially finding or approximating derivatives, we are finding actually the slope or the average rate on a very, very small interval. The tolerance is actually the size of that interval that you want to use. And again, this nderiv command is an approximation technique. It does a very good job of approximating it. In fact, for most functions, we'll find we get the exact value. In other functions, it might be just off just a little bit. But for the most part, what we're going to work with in here and the functions we're going to deal with, it's going to give us enough accuracy. Within 3 decimal places, we'll easily be accurate to that far. Now, if you leave off the tolerance, then it uses a default tolerance of 0.001. So it's a pretty small interval. And for most functions we're going to deal with, that's a small enough interval we don't need to mess around with it. So most of the time we won't specify tolerance. In fact, I can't think of a time where we'll need to specify the tolerance. Now, one other thing that we should note here is the relationship between this nderiv command and finding the derivative at a point that we learned about in the last section. If you recall, f prime of c was defined as a limit as x goes to c of f of x minus f of c all over x minus c. Well, it turns out that's exactly what nderiv does for us. It basically determines a very, very small interval, that slope. The change in the y values over the change in the x values is really what's going to take place there. So what I can say here is that f prime of c is equal to this nderiv command right here. Okay? And so the parts of the nderiv command, notice that in nderiv, the first thing you specify is the function. That's the function you want to find the derivative of. Then you specify the variable that that function is defined on, in this case x. And then finally you specify the value that you want to find the derivative at. In this case we said c, because we said f prime of c over here on the left. Now this nderiv command, we've written it down here this one time, and I'm going to write below this, do not write this. And that's because of the fact that we don't write that nderiv or any calculator notation for that matter on our paper. The only thing I want to see is the f prime of c. That's the mathematical notation that we use to indicate a derivative. And as long as you write down that, that's the work part of this, and then you can let the calculator crunch that nderiv and then write down the answer that it gives you. Let's try an example of that. Take a look at this function here. F of x is equal to x squared. And we want to find f prime of 5. So f prime of 5 is equal to, now again, if you were working in the last section on a problem like this, you would actually have to go through that limit as x goes to 5 in this case, of f of x minus f of 5 all over x minus 5. And you have to solve that out step by step to find out what this is equal to. We're going to use our nderiv command to do this. So on your calculator, let's switch over to the calculator. You're going to find this nderiv command under your math menu, and it's number 8 on your menu. And if depending on which mode your calculator is in, if it's in the math print mode, it'll show up a little bit different on your home screen. I would suggest that you go into your mode, and actually if you go to the second screen in your mode, you can change it over to classic. I'd suggest you do that for right now. You can always switch it back later until you get used to this command. But nderiv, the first thing you specify is your function. So my function is x squared. Again, if that function you'd already put into y1, and maybe you graphed it, did something with a table, whatever you did with it, you could specify y1 right here in the nderiv command, so I don't have to retype that function. It's just x squared, and we haven't put it into y1, so that's why I'm going to type it in this time. The variable is x, and the value was 5. We wanted f prime at 5. And here's an example where the calculator did an excellent job of approximating that derivative, because not only is that a very good approximation, that's exactly the answer. F prime of 5 is exactly equal to 10. Again, most of the time we're going to find it gives us the exact solution. And basically for everything we're going to find it's at least within 3 decimal places of the correct solution. All right, so there we go. There's f prime of 5, and that is sufficient work. You've got your work of f prime of 5, and you've got your answer of 10. All right? All right, so that brings us to then this idea of a derivative function. And when we talk about a derivative function, we're talking about starting with some function f of x, and then using that to come up with this new derivative function. So what is the derivative function? Well, here's how you actually find, or what a derivative function actually is. A derivative function is found by finding the derivative at every single point on your function f of x. So start out at x equals 0 and find the derivative. Then at x equals 1, find the derivative, and so forth. X equals 2 and x equals 3. Find the derivative at every single point on that function. Or probably more likely on a group of points. You're not going to find it at every single point, but on a group of points. And then what you want to do is plot those points as new x y values. So the x value where you found the derivative, and the y value is the derivative that you found there. Plot those as new points, c, f prime of c. And then sketch a curve that goes through those points. So let's illustrate that with an example here. Let's say that we have this function. Looks like a quadratic function, looks like a parabola. And let's say that we want to look at the graph and come up with a set of points that the derivative would actually go through. So I'm going to start out actually at x equals 1, just because it's, I think, graphically the easiest one of these to work with. But at x equals 1, I can see that's the point right here where we hit our minimum. I'm going to go ahead and sketch a little tangent line so we can see that there. That's where our function hits its minimum. So it looks like the slope there, the tangent line, is a horizontal line, so the slope of that is 0. So the derivative is 0 there. So I'm going to just say over here at x equals 1, we got that our derivative was 0. And then let's jump to x equals 2. I'm going to go to the right here, I guess. So at x equals 2, I'm just going to kind of approximate this. Again, I'm just going to kind of sketch in what the tangent line would look like there. And that looks approximately equal to about a slope of 1. Now, if you want to get a ruler out and get a little better approximation of it, calculate a couple points that the tangent line goes through and rise over run, whatever you want to think of it as, you could do so. But it looks very close to 1. So I'm going to just say it's approximately equal to 1 there. Let's do the same thing at 3, at x equals 3. If I were to plot this point and then sketch the tangent line in there, I can see it's an even steeper slope at that point. And so it looks like the slope there may be actually equal to 2. And now let's go back the other way direction. Let's take a look at 0, at x equals 0. Looks like we have a slope here. Looks like there's actually some symmetry to our graph there, right? So it looks like that's probably a slope of -1. And let's take one further step back here to x equals -1. And it's not a very good tangent line, but that'll do. Again, that looks steeper than the first tangent line we sketched there at x equals 0. So I'm going to say that's about -2. And now what we want to do is go through and plot these points. We've got a set of x and y values here. Let's just go through and plot those. So at x equals -1, or c we said is equal to -1, the y value is -2. So I'm going to just plot a point right there. At x equals 0, we got a -1. At x equals 1, we got 0. At x equals 2, we have 1. At x equals 3, we have 2. Okay? So there's a very good sketch, well, not sketch of the function yet, but there's a series of points that our function goes through. And now let's sketch a curve, or really it looks like a straight line in this case, that would go right through those points. So I'm going to kind of try to sketch a line that goes through those points. So this is what we're calling f prime of x, our derivative function. And again, the original function is f of x. That's exactly what a derivative function is. It represents the derivative of a function f at every single point. All right, let's take a look at an example, and we'll actually sketch a derivative function here in this example. In example 1 there, they give us a function. It's a cubic function. F of x is equal to x cubed minus 5x squared minus 8x plus 70. So there's our function. And for part A, it says plot the graph of f and f prime, that is the numerical derivative of f, on the same screen. Well, let's take care of the first of those two. That we've done many times, so let's try that out. Let's take our function and punch it into y1. So in y1, we want to put our equation here of x cubed minus 5x squared plus, or excuse me, it's minus 8x, and then plus the 70. All right. Now, a nice window to see this in. You could start obviously with the standard window and see how that works. It's not going to be the best window to see this graph. A nice window that actually works here is from -3 to 7 for our x's. And you could use your table to kind of find out a good window for the corresponding y's, but it turns out -20 to 100 is a very good window to see this in. And I'll set the scale there for my y's to 100 as well. Now let's just graph that and see what we end up with. There we go, nice, very nice cubic function there, just like we would anticipate seeing. And the next part of this is said to graph f and f prime. So the next question is, how do I graph the derivative function? And they even give you a hint that you want to sketch the numerical derivative. Well, let me come back over here to our notes and just write down what we've done so far. We said that y1 is equal to our function f of x. And in y2, I want to put the derivative function, and they said we're going to use the numerical derivative. So I know it's going to be the nderiv command that I'm going to put in here. All right. And it's the nderiv command. I want to find the numerical derivative of f of x, which was actually put into y1. So I'll specify that y1 is my function there. And then my variable, of course, that's defined on. It's a function of x, so the variable is x. Now, for the value, I want to actually find the derivative at every single value. For every single point that I plot, I want it to calculate the corresponding derivative there. So I actually need a variable that's changing. That starts out at x equals -3 and then changes to the next x value and so forth, moving from left to right. And actually, x is that variable that does that. When you graph a function, your calculator is actually changing that variable called x on your calculator. So actually, if I graph y2 is this nderiv of y1 comma x, we will actually get a sketch of the derivative function there. It will be the numerical derivative, of course, that we're sketching. So let's try that out. In y2, nderiv, my function is in y1, my variable is x, and my value is x. And we'll go ahead and graph it. Now you'll notice that it'll take a little bit of time to sketch this, and the reason for that is because of the fact that, first of all, it's got the nderiv command in there, which takes a little bit of time to crunch those numbers. But on top of that, it's referring back to function y1, so it takes a little bit more time even. But nonetheless, we get a very nice sketch of this function. So there's our function and our derivative function. All right, take a look at part B. It says for part B, f is a cubic function. Definitely you knew that from the equation they gave us, and sketch even verified that. What type of function does f prime appear to be? Well, that's interesting because we started with a cubic function, and it appears like the derivative function turned out to be a quadratic function, a second-degree polynomial. Let's go ahead and write that down, that b, f of x, is cubic, and that f prime of x is quadratic. In terms of polynomials, that is, we started with a third-degree polynomial, a cubic function, and we ended up with a second-degree polynomial, a quadratic function. It appears like when we took the derivative there, we lost one in the degree of our polynomial. That is an interesting feature that we just noticed. Look at C. It says trace to find values of f of 3 and f prime of 3, and describe how f prime of 3 relates to the graph of f at x equals 3. So let's go back to our calculator here. And let's just trace this. I'll start with function f here. And we'll trace it to at x equals 3. You can just simply hit trace and then type in 3 and press enter, and it'll trace to that value. So f of 3 is 28. So part C, f of 3 is equal to 28. And let's also have the calculator find for us f prime of 3. So I'm going to jump down to f prime and just type in 3, and I get it's hard to see that. That is a negative 11 there. We are below the x-axis, so that's a negative 11. F prime of 3 is negative 11. My cursor was right on top of that minus sign. All right, we get a negative 11 there. So notice that's the nice thing about having that derivative function is I can quickly find the derivative at many points. I don't have to go through that entire limit process here to find the derivative at all those different points. So it turns out that f prime of 3 is a negative 11. Now it also asks us then to describe how f prime of 3 relates to the graph of x equals 3. Well, we've talked about this back in chapter 1, but the derivative is negative here. The rate of change is negative. And we said that if the rate of change is negative, then our function must be decreasing. And that's what we see there. Our function f of x was decreasing, and thus f prime of 3 is negative 11. So we can indicate that relationship here. F of x is decreasing at x equals 3 because f prime of 3 is less than 0. It's equal to negative 11, but the key that is there is that it's negative. All right, take a look at part D. D says, for what values of x does f of prime of x equal 0? So again, let's jump back to the calculator. Let me write that down. Then we're trying to find out where f prime of x is equal to 0. By the way, that's sufficient work to write down. I can then let the calculator help me solve that. This is the work, and the calculator will, I guess, do the work of solving that for us. All right, if I look at the graph there, I can see there's two locations where the derivative, that parabola, crosses the x-axis, where it's equal to 0. There's one that looks like it's somewhere back here around negative 1, and there's another place over there about at x equals 4. So let's find out what those values are. On your calculator, if you press second calc, your second and trace button, there's a 0 command on there. So I can have it calculate a 0. Jump to the second function, of course. Press your down arrow to jump there. And again, I said that the solution there looks like it was somewhere around negative 1. So let's give it a left bound of negative 2. You could use your cursor and trace back there and then press enter, but it's much faster to just type in values. And a right bound of 0. And we'll give it a guess of around negative 1. That's what it looks like. And it's actually a negative 2/3, actually. So solution x equals negative 2/3. Now that's one of the two solutions. Let's go back to the calculator and let's find the other solution. So second calc, and we'll calculate another 0. Make sure you jump down to y2. We'll give it a left bound. Again, this time it looks like the solution's somewhere around 4. So let's give it a left bound of 3, a right bound of 5, and we'll give it a guess of 4. And we'll let it crunch its solution there. And notice it gives you 3.9999. That's a good indication that the calculator is actually, it's of course giving you an approximation. So it didn't quite get the exact solution here. It's a good indication, though, that the answer is supposed to be at 4, and that is actually where it should be. So just kind of watch that, because of the fact that it's giving you an approximation with that technique, using your calculator to numerically solve it. But we get those two solutions. All right, so there's also there, what feature does the graph f have at these x values? So now let's check out what function f was doing at these zeros. So if I jump to function f, let me go back up here and just trace this to 4. Notice that at x equals 4, that the function f of x is at a minimum. You get that lowest point. And if I trace this to negative 2/3, notice that f of x was at its maximum right there, at its high point. Which shouldn't be too surprising to us, knowing what we've just done here by finding where f prime of x is equal to 0. I'm just going to roughly sketch our function here for this example, but it does something like this. And if we were to calculate the derivative right there at negative 2/3, again, the fact that it's a maximum point there tells me that this graph actually hit a high point there, and thus has a slope of 0. The tangent line has a slope of 0 there. And that's what we did. We were finding where the derivative, the slope of the tangent line, is equal to 0. So we got that value. And the same thing happened right here. At x equals 4, the slope there is equal to 0. Thus we found those two solutions there. So it turns out that f of x has a max at negative 2/3. I'll go ahead and write this down. F of x has a maximum, I'll just say max, at x equals negative 2/3, and a min at x equals 4. So those zeros of f prime tell me something about the mins and maxes of my function f of x. Pretty interesting. All right, take a look at the last part of this example. It says for part E, plot the graph of g of x equals f of x plus 10. It later asks you in this question how the graph of g is related to the graph of f. So if we go back and recall what adding 10 to a function does, adding 10 onto a function is a vertical translation. It's a vertical shift. It's going to shift it up 10 units. So this is a vertical translation of 10 units. It's going to shift it up 10 units. I should say up 10 units. Up. Okay. And so let's sketch it. That's what they wanted us to do. So we'll add this to our y equals menu. Instead of retyping that whole equation, though, I'll tell it to take y1 and add 10 to it. You could say y1 of x if you want to use that function notation, but just saying y1 is the same as saying y1 of x. And let's go ahead and graph that, and I'm expecting to see this function f of x just shifted up 10 units. And that's what I see there. All we've done is shifted up 10 units at every single point. All right, the second part of this says to also, on the same screen, plot g prime. So if we consider what g prime of x is, g prime of x, of course, is going to be the slopes of this function that we just defined. So if we take and compare, let me go back to my graph there, if you compare the original function f of x with g of x, all we did was shift that function up 10 units. we didn't change the slope of the function at all at any one of those points. We just shifted everything up. In other words, we should expect to get the exact same function as f prime when we graph g prime. It appears as though g prime of x should equal f prime of x, just based on the fact that we didn't change the slope at all. When we graph this new function g, all we did was shift everything up. Let's see if that's what happens. Under your y equals menu, we'll add another nderiv command. And this time it's y3 that contains the function we want to find the numerical derivative of. My variable is x and my value is x. And in fact, since I'm pretty sure we're going to get the same graph right on top, let's change this style that it graphs with. So it draws a little circle there as it's sketching this function. And let's go ahead and graph that thing, and look at there. That's exactly what we thought was going to happen. We were pretty sure that when we sketched this thing, that g prime was going to equal f prime. And that's what that graph there shows us. All right? And that's what the last two parts of part E ask you about, the relationship between f and g, and the relationship between f prime and g prime. All right, that is the end of this section for us.